Hello, welcome to lecture 8, area and volume. This is a continuation of our last lecture. This is part 2 of 2 parts. This is mathematics for class 9 based on NCERT syllabus. My name is Sangam Banerjee and details are given below. Okay, today I am going to talk about surface area of a sphere. In my last lecture I had assumed surface area of a sphere to be 4 pi r square. So now let us prove how to get the formula for the surface area of a sphere. Okay. So this I have taken a sphere and I have cut here, okay, into 4 parts, okay, and this is an octagon. So if I can make these sides smaller and smaller, it will fall on the circle, okay, or these faces in 3D will fall on the sphere. So let us do some approximation here. So I approximate first to begin with. This is a cone. Okay, this is a cone. This is a slanted length, this is the base. Okay, this is a frustum. S is again a slanted. All S's are same. These sides are same, and this is the base, and this is the bigger base, and this is top. Frustum means the top cone is cut, and again similar frustum and similar cone. So surface area of this structure is area of a cone. This. Then area of a frustum, this one, then area of frustum 2, this is second frustum, and this is the area of cone 2. This is cone 1, this is cone 2, and there are 2 frustum. What is the area of a cone? It is pi r1 times s. S is a slant angle, which we have proved it. And area of a frustum is pi times, this is the radius r1 plus r2 times s. S is again this slanted length. Then similarly, frustum, area of a frustum, this one is r pi times r2 plus r3 times s, and this is the area of a cone. So if you add it, you have surface area of this kind of a structure will be 2 pi s times r1 plus r2 plus r3. Now let us see this figure and try to see some relation, and it will be a good recapitulation of what we did about congruency and similarity of a triangle. So if you see that if I draw a parallel line here, this angle, and suppose this is a traverser. So this angle, this is the internal angle of this traverser, and this is the internal angle of these 2 parallel lines. So these are alternate interior angle are same. So this angle and this angle is same. Now these are isosceles triangle, same length of the S. So this angle will be equal to this angle. This is 90 degree, this is 90 degree. This triangle, you can show here, even this triangle, you can show, they will all be congruent. Now I am taking this and this like this. So this angle will be equal to this because this is the internal angle. And since this is a diameter of a circle, from any point to the extreme end of this diameter, if you draw, this has to be 90, which we have proved in a theorem. So this is 90, here also this is 90. So this triangle and this triangle are similar triangle. Similarly, this triangle also, okay, here, this triangle. This angle will be same, this is 90 degree, this angle ABC will be 90 degree. This is the same triangle here, okay, just rotate it. So even this triangle and this triangle will be similar, okay, because this angle, they are same. So since sum of internal angle has to be 180 degrees, so this angle and this angle. So from angle, they are similar triangle. So R1 they will all be in same ratio. So R1 by A1 will be R2. This is the radius R2 by A2. Similarly, your R3, this is the same. R1 is equal to R3. So R3 by A3. So here I have written R1 by A1 is equal to R2 by A2 is equal to R3 by A3. So similarly, this AB by BC, okay, which I have taken here, R2 by this is the base A2. So this is the base of the triangle. This is the height, altitude. So this divided by this AB by BC, okay, they all will be equal because they are similar triangle, and that equal to AB by S because BC is S I have taken. So we can find R1, R2 and R3 for this equation. R1 is AB divided by S times A1. R2 is AB divided by S times A2, and R3 is AB divided by S times A3. Okay, So here I have written R1 plus A. So AB divided by S times A1 plus A2 plus A3. This is 2A1 plus 2A2 plus 2A3 is diameter. So A1 plus A2 plus A3, this is half of it, will be half of AC. Okay. So I write A1 plus A2 plus A3 as half of AC. So surface area is from here 2 pi S I have written. R1 plus R2 plus R3 I got this. So I substitute here. Okay, I get AB by half AC. So this S get cancelled. This 2 get cancelled from here. So I have pi AB times 2R. So as S tends to 0, then this AB will fall on the diameter. This AB, the length of AB will be equal to the diameter. So I now write diameter is twice R. So I write pi times 2R. AB as substitute as 2R. That is the diameter times 2R here. So I get 4 pi R square. So as number of sides, that is as n tend to infinity, AB equal to AC equal to 2R. Now let us talk about volume of a frustum. So volume of a frustum is, this is the frustum, the shaded region. So you chop off the cone, you get the volume of the frustum. So volume of a frustum DEBC is volume of the cone, that is big cone, minus the volume of the small cone. Okay, so what is, now this is very simple. What is the volume of a cone? We have seen volume of a cone is 1/3 base times height. Base is pi r square. R is the radius, capital R. We consider only the big R here. Pi r square, 1/3 pi r square, h plus a. This is the volume of the big cone. And what is the volume of the small cone? Is 1/3 pi small r square times a. Okay, 1/3 base area times height. Okay, and the volume will always have a dimension of cube. So this is R is a dimension, is a length dimension, and this is also length. So length square plus another length is length cube. So volume will always have dimension of length to the power 3. Area will have only dimension of length to the power 2, which we will see when we do physics. Okay, so pi by 3 is common, r square times h plus r square times a, and from here pi by 3 is common, so I have written minus r square. So again I rearrange it and I can write it like this. But this, in this triangle, this big triangle, okay, projection of the cone, and this small triangle, they are similar because this angle is same. This angle is same. So from angle, this triangle is similar to this triangle. Okay. So since these are similar, that means I can write A by R is equal to A plus H by capital R. I can write like this, what I have done earlier. See, I want to get rid of this A. So that's why I am now trying to get, I will substitute this, I will find out this A in terms of what we know. We know this R, we know height, and we know this. But we don't know A. So how to get rid of A, that's what I am trying to show you. So volume of this DECB, that is DECB, this volume of the frustum, is nothing but, here I substitute this value of A here, what I have written here, because I don't want to know, because this is not there, this is vanished, so only this much is there. So I substitute this here and I can get as 1 by 3 pi, this is the volume of a frustum, pi times height, height is, this is the height or altitude you say, r cube minus big R cube minus small r cube divided by big R minus R. So this is the volume of a frustum. So now we'll talk about volume of a regular tetrahedron. This is slightly complicated. Go through it very slowly. I will try my best to explain you. So I am not, as I said, not good at drawing. So you see here, this is, I have tried to draw tetrahedron. This is the base. Okay, A, B, C is the base. And this is a tetrahedron. This is one face in the right hand side. This is one face left hand side, and A, D, B is the back side. So they are all of same length here. These sides or edges are same A. So this is also A. This is also A. This is also A. Okay, and this is the slanted length L. This is L. These are A. This is half A by 2, that is, this total is A, and this length, this is perpendicular, so it will go to a vertex. This L is this, and you see from this centroid I have drawn one circle here which is touching tangentially to these three sides here. and this is the altitude, height h. So volume of a regular tetragon I can find as like volume of a cone. We said 1/3 times base into height. That was even we found for square base pyramid, 1/3 times area of the base time height. So similarly here also you can show, as we have done in earlier cases. I am not going to repeat, with those blocks, make thinner and thinner blocks, and you can show that it is indeed 1/3 area of base into height. So this is for all this kind of conical structure, whether this is also a conical structure tetrahedron, or square base tetrahedron, or circular base cone. Okay, so they will all have same which we have shown earlier. So area of a base of this tetrahedron, and if you know these sides as A, in principle you can find the area of this base using Heron's formula, but we do not know what Heron formula is. We will deal in the next page. But suppose we don't use the Heron's formula, and we also do not know what is the height. So we have to find this height, and we have to find the area of the base. So how you go about doing it? We will use Pythagoras theorem, which we will also prove. Okay, from Pythagoras theorem tells you that this length, this, if suppose is a right angle triangle, this a by 2 square plus l square is this a square. The bigger a square is, the bigger length square is equal to sum of other two smaller length square. Okay, so this is what I have written here. A square is equal to a by 2 the whole square plus l square. So I can know this L is the slanted length, and this is A. Okay, and I am drawing a perpendicular, and this is an isosceles triangle. So we know this is, it bisects, it's perpendicular. That all we have studied. Okay, so we will not repeat it again here. So this, now how do you find L in terms of A? So L, here I write L square is equal to A square. I take this in the left hand side, and I just A square, that is 4a square minus a square is 3a square by 4. Okay, so L is equal to square root, because it's L square here. Now we have found L is equal to this. Now we have to find this distance from the centroid to the edge of the tetrahedron. That's the tangential point here, and once I know this distance, I can find the altitude. So I take this triangle here. I have shown it here. I have blown it and shown it up here properly, and I take this triangle AFE. This is a small triangle AFE, and this is a big triangle AFE. They are similar triangle. Why they are similar triangle? Because these angles are common. This angle is this angle, so they are common. Okay, and since I have taken as a midpoint, AC is equal to twice AE, and AB is equal to twice AF. So similarly, BC will be twice FE. Okay, and also triangle FEG, this triangle, you see this triangle here, FEG, and triangle CBG, they are also similar. How they are similar? Because these are two parallel lines. So this angle, this is a internal alternate angle. So this angle is same. This angle and this angle is same. Okay, and this opposite angles, these are the opposite. This, when you cross it, this angle same. So from angle they are similar. So now this, since BC is equal to twice FE, this base and this base, the triangle, this is a one triangle and this is another triangle. This base BC is equal to twice FE, which we have proved. So similarly, they should be all be in the same ratio. Okay, so that means this BG will be twice of GE, and similarly this GC or CG will be twice of FG. Okay, so these lines are the median. What do median means? A line goes to the centroid. Actually, it cuts the triangle into two equal halves. So similarly, AH is also a median which passes through this centroid. So the centroid divides each median. This is BE, CF and AH. This is BE, CF and AH. Okay, into a segment with 2:1 ratio. Okay, so this is twice 1. So this is twice and 1. So this is the L. So the in radius will be 1/3 of the L. So this is L. So this is 1/3 because this is twice. So now we have found L. We know A. So we can find h now. This is known. So here what I have written here, 3 by 4 times a square is equal to h square plus this. So similarly h square is this. I bring this a by 12 left hand side, it becomes minus. So a square is common. Okay, so this is, if I do some little algebra, I will get h as square root of 2 by 3 times a. Okay, so I now have got h also. So what is the volume of a tetrahedron? I said it is half time area of a base times height. So I have got the height, the altitude h from here. What is the area of the base? Area of the base is half times a times root of 3 by 2. This is the area of the base of the triangle. I have put it here. So 1/3 base into height. So I get the volume of a tetrahedron in terms of A. Similarly, we can also find the area of a tetrahedron. How do you find the area of a tetrahedron? Area of a base, all faces are this. So how many faces are there? 4 faces, 1, 2, 3 on the top and 1 bottom. So 4 times this. So this is the area of a surface area of a tetrahedron. So now we discuss Pythagoras theorem. We have discussed Pythagoras theorem earlier, which we said orally, but now we will write it down. What does the Pythagoras theorem says? That square of the hypotenuse is the sum of the squares of the other two sides. So that is AC square is equal to BC square plus AB square. So this is what we will prove it. AC square is AB square plus BC square. So this, how do you prove it? Very simple it is to prove. And since we have taken a right angle triangle, so this angle plus this angle plus this angle is 90 degree. Now since these are similar triangle, I can write this big triangle and small triangle, this, suppose this part AB divided by AD will be equal to BC divided by DB. That will also be equal to AC, this hypotenuse divided. Because they are similar triangle, they will have the same ratio, okay, between their corresponding parts. Okay. So what I require some squares. So I can see here AB here and AB here. But others I don't see anything common. So AB is common. So AB square is equal to, I don't require this, then AB square is equal to AD into AC. So I write AB square is equal to AC into AD. Similarly, I can compare triangle 1 and 3. Okay. Again, I can write similar thing, AB by BD. This is BD. And then again similarly, I write BC by DC equal to AC by BC. Okay. And I get here, I see that BC, there are common here, 2 BCs are there. So again, I can write BC square is equal to AC into DC. So BC square is equal to AC into DC I can write by cross multiplying. So I can sum this one AB square plus BC square, that is AB square plus BC square is AC into AD plus AC into DC. AC is common, so I take AC out, AD plus DC. And what is AD plus DC? AD plus DC is AC. So I have AC into AC. This is AC. So I have AC square. So I have this formula, AB square plus BC square is equal to AC square. You can visualize it in another way also. Suppose you have a square. Okay, this is a square, say, and I make inscribe another square here. Okay, with length each side as C. And I make this in such a way, this side is A and this is B. So A plus B. I in this ratio I put the dots here and join this equal this is. So now I have how many triangles? I have 4 triangles, 1, 2, 3, 4. Okay. And what is the area of a triangle? We have said half base into height, that is half A times B. So how many 4 are there? 4 times half A times B, and 1 square is there. So area for this big square is A plus B side is A. So A plus B into A plus B is A plus B the whole square. So that is 4 times the area of these small triangles plus the area of this square. So what is the area of this square with the side A plus B is A plus B the whole square. We will see this expansion in the next chapter, how we do, and more complicated ones we will do. This is the most simplest one. So you have A square plus 2AB plus B square is equal to this 2 get cancelled, 2AB plus C square. So now this 2AB cancel, so we have A square plus B square. So again very similar Okay, this is the Pythagoras theorem. That is a square plus b square is equal to c square. This is an example. Find the area of a cross section at a distance h from the center having radius r. So this is the radius r for sphere, and this is from the center. This is the distance h. So it's telling you, asking you what is the cross sectional area of this cut. If I cut it, what is the cross section area? This is the example for how these Pythagoras theorems are used. So this is what I am showing here. So this r square is equal to h square, and this radius I do not know. I call it x square. So r square is h square. This is the bigger. This is the hypotenuse. Okay, this is the biggest arm of the triangle, and these are the other two, the smaller ones. So r square is h square plus x square. So I bring this h square in the left hand side, and so x square will be r square minus h square. So x will be square root of this. So the area of a circle, this cross section at h will be pi times this x square. So x square is r square minus h square. Okay, now we come to some theorem and examples of chapter 9. Remember, area of a parallelogram, we said it is base times the altitude, this height, not the slant, the altitude. So a times h. Okay. So now we come to theorem 9.1. It says parallelogram on the same base and between the same parallelogram are equal in area. Yeah, that is, suppose this base is same and I have this parallelogram here. Okay, A, B, C and D, and I have another parallelogram E, F, D, C. Then the area of both these parallelogram are same. That is, to prove area ABCD is equal to area EF. So area we will write in short as AR in short. So here you see area of ABCD is equal to area of this triangle ADE plus area of this quadrilateral. So area of this parallelogram ABCD, area of parallelogram, is nothing but area of this triangle, that is ADE plus area of EDCB. Okay, this is the area of this. So this area plus this area is the area of this parallelogram, and the area of this parallelogram is this area plus area of this quadrilateral plus area of this triangle. So this area of this quadrilateral is common in both. So we have to show, since they are common, so we have to show this area of this triangle and this triangle is same. So that we can show very easily. So in this figure we see that if I draw, this is a parallel line they have asked, they have said. Now if I draw a traversal here, another parallel traversal here, this angle will be equal to this angle. Similarly, if I draw a traversal here between these two parallel lines and same traversal parallel to this, so this angle will also be equal to this, because as you know, sum of all internal angle has to be 180, so it has to be constant. So this angle and this angle will also be same. And so this, since this angle and this angle is same, this length, and this is the parallel line, so this length and this length will be same. Similarly, this length and this length will be same. So from side, angle, side, these two triangles, side, angle, side, they are same. So one can show that these two triangles is congruent. So since these two triangle is same, so this plus this area will be same as this, because this is common, plus this area. So here what I have written. So how do you show that? I have shown that because AD is equal to BC, this AD equal to BC, from opposite side of the parallelogram are equal. So this is a parallelogram, they are equal. And angle DAE, which I have said is equal to CBF, and angle AED is equal to, that is AED is equal to this angle. So angle ADE also will be, okay, sum of the property of a triangle. So therefore triangle AD is congruent, areas are the same. So the area of a parallelogram, these are same. Okay, this is what I have written. Just freeze it and see it, what I have said. Now example 9.3.2. It says, or it asks, if a triangle and a parallelogram are on the same base. So this is the base, same base, AB. If this triangle and this is a parallelogram. This PAB is a triangle and ADCB is a parallelogram. They are in the same base and between the same parallel line. Then prove that the area of triangle, prove that the area of the triangle is half the area of a parallelogram. So by now you all should know that, okay, area of a parallelogram is, as I said, base into this altitude. And area of a triangle is half time base into altitude. So definitely this, so now let us prove it. We know it, but how do you write it? So what we do a trick is we draw one more parallelogram, this in dashed line, parallel to this AP as QB. We have seen from earlier theorem, if two parallelograms are between two parallel lines with the same base, then the area is same. And we know that if you bisect a parallelogram, you will have two equal parts. So this will be half the area of this parallelogram. Okay, so this is very simple, we have said, so you just simply write it, that area of ABQP is equal to area of ABCD by theorem 9.1, which I have said, and area of PAB, this area of PAB, this triangle, I should have shaded it, this triangle here, is the area of this parallelogram ABQP from the diagonal of parallelogram divides into two triangles. So area of this PAB is half the area of ABC. Now exercise 9.2.1, okay, this is a figure given in the textbook. I have not written what it is written. It is asked to find what is the distance AD. It is given that this one is 10 centimeter if a parallelogram you draw, and this is 16 centimeter, and this is your 8 centimeter, this altitude, and this one is 10 centimeter. So we know that area of a parallelogram is base into height. Base is 16 centimeter. This is your base, DC is your base into height, is equal to, again height is given for this parallelogram as 10 centimeter, which we have to find AD. So I do cross multiply, AD I keep it here, I bring 10 centimeter down, 16 by 8 by 10 centimeter square centimeter. So AD is 128 by 10 centimeter. So that is 12.8 centimeter. Okay, this is how you should do the problem. You should write also the unit. So then you, since they have given unit, you too have to write the unit. Now theorem 9.2, two triangles on the same base or equal base and between parallels are equal in area. That is, these two triangles, suppose this is one triangle, this another triangle, between two parallel lines, they have the, if the bases are common and between two parallel, then they have the same area. So it can be like this also. I have drawn simpler one, but it can be obtuse also. So this area of this hash and this hash will be same. Draw any two triangles with a common base, it will be same area. So we have to show that area of triangle ABC is equal to area of triangle PBC. Okay. So what I do a trick, I extend this parallel line and I draw one more parallel line parallel to this. So I get one parallelogram. Okay. And similarly, I take this line and draw another parallel line. So we have two parallelogram. Okay, one parallelogram is this one, that is ABCD, and another parallelogram is this parallelogram PBCR. Okay, and they are equal because common base and between two parallel, that we have shown using in theorem 9. So half of this area which we have seen earlier, the half of if I cross a diagonal, then I will, this is a parallelogram, if I draw a diagonal, I will get, so half of area of ABCD is the area of triangle ABC. So if half of this parallelogram is area of this, and similarly half of this parallelogram PBCR is, if I cut this diagonal, if I take it, I get this triangle. Okay, triangle PBC. Now I know this is equal to this, okay, because they are between, these two parallelogram are between the same two parallel line and have the common base. So similarly, if this is equal to this also has to be equal to this. Okay. Now theorem 9.3, it says that two triangles having same base or equal bases and equal area lie between the same parallel. It's the same thing vice versa. Okay, that is, it says that equal area will lie. So similarly you can prove almost similar. So this you should do it. It's same as the earlier one. Now example 9.4.3. I have not written, you go through this example in your textbook and see how they have written, but here I have just written is that given a triangle ABC and from point A to a midpoint of BC, that is point D, these are same, then show that area of a triangle between this and this triangle 1 and 2. It is very similar to that. If there is a, suppose I move this triangle here because they are same. So now common base. So now I have two triangle between, and this height is also same. So they are between two parallel line with a common base. So area of triangle has to be same, triangle 1 and triangle 2. Okay, base is BD square and same height. So this is how you can just simply move it and show it. Example 9.4.4. So I have not written again. You please go through your textbook and see what it is. But anyway, you will understand what it has asked. That it has said that proof that area of this quadrilateral A, B, C and D is equal to area of the triangle ADE. Okay. So this quadrilateral A, B, C, D, the area of this quadrilateral is equal to the area of this triangle. Okay, this is very easy to prove. Okay, how do we prove it? You see, this triangle is common to both the quadrilateral, this unshaded triangle, to the quadrilateral as well as the big triangle. So if we can show that this shaded area of the quadrilateral, which appears to be a triangle, this shaded area and this shaded area are same, and this is common. So this area plus this area is the area of ADE, and this area of this triangle unshaded plus this is the area of the quadrilateral triangle. So we have to prove that this area of this triangle is equal to area of this triangle. So now you draw a parallel line here. Okay, and you see this is a common base of this shaded triangle here, this triangle and this triangle, this is a common base and this is a parallel line. So we have shown that if there is a common base and between the two triangle lie within the parallel lines, so this area has to be this area. So that since we now know that from the theorem this area is this area, so I add this plus this, I get the area of a quadrilateral, and this area plus this shaded area, I get the area of triangle. This is what I have written here. Area of ABCD is equal to area of ADC. This is area of ADC, the unshaded region, plus ABC. Okay, this is for the quadrilateral. And area of triangle AD is again area of ADC. This is ADC plus AEC. So therefore, this area of quadrilateral ABCD is equal to area of triangle ADE. Okay, just freeze it and go through it. Okay, now we deal with area of a triangle by Heron's formula. Okay, this is for completeness sake, since I have mentioned earlier that Heron's formula can be used for calculating the area of a triangle. In a Heron's formula, you only require to know you don't have to know the height, but just all the side if you know, then you know the area of a triangle. So area of a triangle here is not like half base into height. Suppose you don't know the height, then from the sides you can know. So let me show you what the formula looks like. So this is a formula, square root of s minus a times s minus b times s minus c times s, where s is a plus, this is called the semi-perimeter, a plus b plus c by 2. Of course, a can be equal to b equal to c, then it becomes a equilateral triangle, or you can have isosceles triangle, but here this is a general form. So area of a triangle is half base into height, we know, and we have to prove area of a triangle in terms of sides only. So here we see this is the triangle, different length a, b and c. We have done the Pythagoras theorem that b1 square plus h square is equal to a square, we know. So height is, I can bring b1 square this side, so h square becomes h square root of b1. So this we know, but here you see now b1 is coming. Okay, I have drawn a perpendicular b1. We do not know what b1 is. We have to get rid of b1. Okay, so how do we get rid of b1? We know b1 plus b2 is capital B. This is what we have done here. And b1 square plus h square, which I have written is equal to h square, and b2 square plus h square is equal to c square. So I write b1, this I subtract it, h square gets cancelled, b1 square minus b2 square is a square minus c square. So I now can factorize this. We will see these things in next chapters. Okay, so now for timing you assume it, a square minus b square, if it is something like this, a minus b into a plus b. So here b1 square minus b2 square is b1 minus b2 into b1 plus b2, that is equal to a square minus c square I have written here. This will prove it. You can just also see here b1 square, b1 into b1, then b1 into b2 is b1 b2, this is b1 into b2, plus minus get cancelled, and minus times b2 into b2 is minus b square. So this is what you get it here. Okay, this is how you can factorize it. So I simplify further. b1 minus b2, b1 plus b2 is b, I know, is a square minus c, and b1 minus b2 is a square minus c square by b. I get the b here. And similarly, b1 plus b2 is b, I know. So I cancel this b2 here. So I can write b1 in terms of a, b, c and b, all the sides. So area of triangle ABC is half time base into height. Base is this b, and h we know that it is a square minus b1 square root of this, which we have shown here. Okay. So I substitute now this h here, a square root of a square minus b1. And now this b1, I write here half b, and h is nothing but this a square minus this b1 square. This b1 is given here. And since this is 2b square, I have made it equal. So I have multiplied and divided by 4b square. So I have this half b by 2 here. And under the square root, I have taken 4b square common. This is again I am writing as a square minus b square. That is a minus b times a plus b, which we have done it earlier. Okay, for this one we have written this formula. So a minus b times a plus b. So this is 2b a square is 4b square a square. So I have written 2ab. So a minus b, this is square. And this 2b is outside, this is also outside, so it is 4b square under the square root. Okay, so now that this is under square root b square, square root of b square is b, that this b and b get cancelled, and I bring this 2 inside the square root. So 4 into 4 16, so I write like this. I rearrange it, just freeze it and see. Okay, and if you don't understand now, maybe after we go to the other class where we do factorization and manipulation of some this kind of stuffs, then you can come back and look into it. So you will, from this step, you will get this is a minus b the whole square. A minus b the whole square is a square minus 2ab plus b square, and this is a plus b the whole square is a square plus 2ab plus b square. So I write like this. Then again I write it, this is again a square minus b square. So a minus b into a plus b. Again this is a minus b into a plus b. So from here you can write c minus a minus b. This I am 16, I am bringing it here, 2 into 2 4 into 2 8, 8 into 2 16. So I am giving 2 to each of them division. So I get this c minus a minus b by 2, c plus a minus b by 2 similarly. And then I can say that suppose S is a plus b plus c by 2, then I can write a plus b minus c by 2 as a plus b plus c by 2 minus c, because this is half here, c by 2, and minus c is minus c by 2, so this is minus c by 2. Just see it, you will understand. This is similarly here also I write it. So this is S minus C, S minus B, S minus A. So this C minus A minus B, that is C minus A minus minus become plus. So this is S minus A. So similarly this is S minus B. Okay. That is C plus A minus B. So C plus A minus B. This is S minus B. And this is A plus B minus C. So A plus B minus C by 2. Okay. So this is S minus C times a plus b plus c. So this a plus b plus c is a perimeter, but divided by 2 is a half, so it's called semi-perimeter. This is the well-known Heron's formula. It requires only the length of each sides, but doesn't require the altitude of a triangle. Okay. So important points on surface area. Heron's formula can be used to find area of any quadrilateral if the quadrilaterals can be broken into triangular parts. So very easy, if there are quadrilateral, so if you know all the sides, so I don't have to measure what is altitude, what is. So this was used in earlier days, okay, and these are used. Suppose you are putting tiles and you want to know the of different this, so you just measure the edges and you get the area of that quadrilateral or any even if it is a polygon, any polygon. You break into triangles and sum up all the areas by knowing only the side. Okay, point 2, total area of any surface can be broken into many parts and then add them up. Okay, so suppose you have a cone and this is also covered. Okay, so I know the area of this cone is say pi times r times this slanted angle L, okay, times pi r square. Okay, this. So say our cylinder is covered here. So this hollow cylinder plus this lid and the bottom lid. So you have to add up all the area. Suppose if it is a hemisphere like this, of course it's hollow. I'm talking about the area only. So area of this top shell and this base. And if you want to know the surface area of a cube or 6 faces structure, so area of surface 1, surface 2, backside surface 3, 4, then top 5 and the bottom 6. So you have to add all the surfaces. Okay, and suppose you have a tetrahedron which has 4 sides, triangle 1, 2, then a front triangle is 3 say, and this is base. So you have to add all the 4 triangles. So that is all for today's class. Thank you. See you in the next lecture.